intuition behind cost function. On the left side is hypothesis function h theta x, it is for fixed theta 1. And on the right side is cost functions of parameter theta 1. So as we can see, given graph with straight line in hypothesis function, the line based on given theta 1 values, which is 0.5, and consider theta 0 equal to 0. So the red cross is the value of h theta equal to yi. To find j theta 1, we need to compute the cost function as given. Cost function is sum of squared values. So as we can see here, j theta 0 theta 1 equal to 1 over 2 times 3, which is 3 is the number of training set, and then we multiply with sum of h theta xi minus yi squared. Here we got 0.5 is a predicted values of hypothesis minus with 1 actual values of hypothesis, and then we squared. Then we plus with 1 minus 2 squared plus with 1.5 minus 3 squared, and we got the answer is 0.58. The answer of 0.58 then labeled on the cost function diagram, which at the theta 1 equal to 0.5. Gradient descent is an optimization algorithm which is mainly used to find the minimum of a function. So here we got the final set where we can see the hypothesis line is quite fit to the training data set when j function located at center of control plug. Another parameter is a learning rate alpha. So by having a small value of alpha, small step will be taken, and this will slow down to get the minimum value of j. So on this diagram, as you reach a local optima, the slope will approach 0. Once the slope of current parameter is 0, the parameter value will stop updating. While this is useful as it results in convergence and signifies that we can stop the iterative process. It can pose a problem when the gradient descent finds a local optimum. To prevent gradient descent from getting stuck at local optima, we can use the momentum term, which allows to overcome local optima. In some cases, we can develop cost functions which are proven to have convex space, guaranteeing that we only have one optimum, the global minimum.
Feature scaling for gradient descent is necessary to make all features in the similar scale. For example, we have problems with a multiple feature. Make sure that the features are on a similar scale, by which make sure that the different features take on similar range of value, that gradient descent can converge more quickly. Okay, let's say in our problem, first we have a size of Houston, which is a value between 0 to 2000, and the next problem is the number of bedrooms with a value 1 until 5. So in the picture given, here you can see obviously that the parts on the left is much longer than that on the right. The scaling is applied to the left to become to the right one. In the left one, it was in slip shape, and the right one, after the after the scaling is applied. Next is multiple features. So here is a formula to find a hypothesis function. As we will use the formula in the once we substitute the value. So for case 1, theta 1 I substitute as 0.5 and theta 1 equal to 0. This is because we don't want any intercept. So our theta 0, so our hypothesis function means hx equal to 0.5 x. So we plot the graph. Okay, 0.5x. So we substitute x with the value 1, 2 and 3. So 0.5 multiplied by x, we will get 0.5. And if we substitute 2, 0.5 multiplied with 2, we will get 1. And then if we substitute 3 in the 0.5, we will get 1.5. Okay, so next, the formula. So here is a formula given. Once we already get the value from the hypothesis function, so we substitute it in the formula. So as you can see, 1.3 as we plot the graph, 3 with the 3 point, and 0.5 once we get the value of x. So then we will multiply with 2 times because as a formula given, 2 multiplied with m, so the solution is 0.58 cos. So that's all from me. Thank you.
Logistic regression cost function can be divided by two parts. The first part is when y is equal to 1 and the second part is y is equal to 0. So when y is equal to 1 and the equation is negative log h of x, as shown in the slide, the graph shows the function h of x is within 0 and 1. Classification are based on these two binary numbers, and based on the graph we can see actual target of y is equal to 1, hypothesis is equivalent to 1, cost is equal to 0, meaning that prediction is correct to the target of y, but at the opposite direction. As h of x goes to 0, the cost becomes larger and may go up to infinity, as shown in the upper part of the graph. We analyze the learning algorithm by a very large cost. So, when y is equal to 0, shown in the second line, while looking at the line, the hypothesis goes fit with the target of y, when now the prediction of 0 by the hypothesis function is correct with y. The cost goes to 0 when hypothesis is 0. Opposite direction or the graph when the function 1 minus h of x goes to 1, the cost function value will go to infinity. This produces larger penalties to the algorithm. This is different than linear regression, and this based on the condition of y. These two functions can be simplified.
Assalamualaikum and hello. My name is Nur Fasniza and I will present about intuition of cost function and example of linear regression of housing price. On the left side for the intuition of cost function, if we were to fit a quadratic function to this data, it gives pretty good fit to the data. Where we were to fit an overly high order polynomial, we get a curve that may fit the training set very well, that really not overfit the data poorly and not generalize well. Consider the following. Suppose we were to penalize and make the parameter theta 3 and the theta 4 really small, where we minimize our user square error cost function and modify the objective plus 1000 theta 3 square plus 1000 theta 4 square. The only to minimize to make this new cost function small if the theta 3 and theta 4 are small. Otherwise, you have 1000 times theta 3 for this cost function. When you minimize this new function, theta 3 close to 0 and the theta 4 close to 0. As we getting rid of the two term at the back of the objective, then we end up with a well fit to the data occur as shown in the slide. For the right side, for the example linear regression for the housing price, where we want to predict the price as a function of the size of the hall. One thing we could do is fit a linear function to this data, and we do that, we get a straight line fit to the data, but this isn't a very good model. Looking at this data, if seen as the size of the hole increases, the housing price kind of flatten out as we move to the right, and so this algorithm doesn't fit the training set very well, and we call this problem underfit and has a high bias, meaning this algorithm doesn't fit this training data very well. In the middle, we could fit a quadratic function to the data, and with this data set, we fit a quadratic function on the curve shown, and the work pretty well. Last one we will fit will be if we were to fit, say, set a fourth order polynomial to the data. So we have 5 parameter theta 0 to theta 4, and with that we can actually fill the curve that passes through all 5 of the training example. We might get a curve that shown on the slide. On the other hand, seem to be very well to fit in the training set, that it passes through all the data at least, but it's still the weekly curve going up and down over the place, and we don't actually think it's a good model for the predicting housing price. So this problem we call overfitting, and this algorithm has a high variance.